Good morning. I'd like to first start off by thanking again, echoing all the thanks for the Black Alps team here. It's a really nice event, so thank you again. We're going to be talking about vulnerability discovery today. So, title of the talk, Needles in the Haystack, a heuristics-based approach to vulnerability discovery. So, we'll get right into it with some quick introductions. I'm Jack Ullrich. I'm a consultant at SpecterOps. I go by Winternal online. I have a blog of the same name, and my background is mostly in malware development and Windows internals.
And I'm Matt Hint. I go by I'm interpreter everywhere. I work at Prelude. Recently wrote a book about EDR. Just got published with No Start. Just came in a couple days ago. Background's in primarily red teaming, but did vulnerability research long time ago. Do a lot of reverse engineering, Windows internals, low-level driver, hypervisor stuff.
Cool. So, I won't spend too much time here, but there's a little bit of philosophy and context for this talk, right? So, the title of the talk does not contain the word research, right? We are not vulnerability researchers. And so discovery does not equate to research. When you think of discovery, it's defined as detecting something new or something previously unrecognized as meaningful. And we have another great AI-generated image here. The immediate example that comes to my mind is the discovery of fire. Right? Fire is and was in the environment waiting to be discovered. I'm not talking about the application or the mastery or harnessing of fire, right? I'm talking about the actual point in time where it was discovered and applied meaning. And then you have research. So research is defined as the creative and systematic work undertaken to kind of like push the boundary forward in a field. It's a little harder to kind of quantify, but I think the picture on the right of the caveman, that's a product of research. Because it was generated by OpenAI, the DALL-E 2 engine, right? That's decades worth of research into machine learning, computer graphics, right? And that produces a product of research. And so what I'm really getting at here is we can think of the vulnerabilities here because we are red teamers. We are not vulnerability researchers, right? We can think of the vulnerabilities as simply being present in the environment, waiting to be discovered by us. And so we don't possess the same skill set as a vulnerability researcher, right? So with that basically disclaimer out of the way, we can kind of come to our initial problem statement, right? The return on investment problem. So red teams are always going to be time boxed. They're always going to be constrained by some sort of resource, time, money, skill level. There's constraints that you have to operate in. The fields of vulnerability research and exploit development don't necessarily align with that, right? When you think of those fields, right, I think of people who are way smarter than me. There's a high barrier to entry, and it takes a lot of time. So as a red teamer, you have to kind of reconcile, right, this really esoteric practice and delivering kind of value. So when you're operating in these highly defended environments, you have to make sure that the exploits you're using are going to be relevant and accessible. So what that means is you're moving past the low-hanging fruit, right? You're trying to come up with new and novel exploits in the environment to help progress and kind of dictate the direction of your red team engagement. So this brings us to one of the first questions we're posing here. How can we maximize our chances of finding an exploitable bug quickly, right? Within the constraints and on an assessment, basically. So the very first step in this is gathering a data set, something to use that we can apply filters on, right? And that step is going to begin with target identification. So to add a little context here, preface to this section, right? We have this concept of a golden image. So mature organizations are usually going to have their endpoint configured and standardized, right, into what is known as a golden image. They're going to have the same software, the same security settings, firewall rules, etc., right? They're going to be vetted for compliance, but not usually audited by like a application security team or maybe an internal red team. And so why is this important, right? Well, it's important because when you assess on the golden image, an exploit will translate right from the individual to the enterprise. And that basically addresses some aspects of the return on investment problem automatically. So when you can, always assess the golden image. So you're on the golden image, where do you start, right? There's no one place to start, and you should ideally do as much as you can. These are kind of very basic starting points. The first approach is just going to be simply walking the file system, enumerating everything that could potentially run, right? Gathering metadata about applications, execution or executables that exist. There are some drawbacks to this method. We don't know if the application will actually run, and we lack runtime metadata too. So just enumerate the processes, right? We actually know what's running on the system, and we can collect the additional kind of runtime metadata present. And then the drawback to that is basically it's a snapshot. It's a point-in-time representation, so it's not continuous, right? But this is very basic stuff, right? It's process enumeration and file system traversal. But it's very useful, and it's sufficient enough to build this data set that we're working with. So when we're walking the file system, when we're looking at processes, what file types are we looking for? So from lowest to highest priority, we're going to be starting with non-executable files, right? We're going to be looking at log files, configuration files, right? Why are we looking at those? Well, they can maybe instrument some part of the application's control flow, right? If they're loading a binary plugin or something like that, we can look at that. If if there's a setting in the JSON configuration file on disk that can instrument some sort of behavior in the application, then we want to know about that. And then serialized data, right? Maybe base64 blob. What's it doing? You're casting the widest possible net here. And then moving on to dynamic libraries, right? These can be thought of as basically runtime dependencies for other applications. Something that we'd like to pay attention to is if DLLs are injected into every process or a very large subset of processes to extend or modify functionality, then we're going to be interested in those. And then, of course, interpreted languages. Languages that are compiled to an intermediate representation. Why are we interested in those, right? We're interested in those because they're easy to reverse engineer, and you can almost always decompile them to a one-to-one representation of the source code. And then, of course, executables and drivers. This is going to be the bulk of our target area. Anything that executes, right? Services, drivers. And then moving on to the highest priority actually is going to be scripts, right? They're plain text. There's no reverse engineering required. It doesn't get easier than that. They're often internally developed. So what I mean by that is that they're developed by people maybe from the IT department or people who generally don't follow proper software engineering practices, right? And then when you think of scripts, they're often going to be performing some sort of management function. And management functions they're often inherently privileged. So you have this trifecta of just, qualities that make for, make for a good target, basically. And so in terms of file characteristics, what are we looking for, right? So like I've said, internally developed tools are going to be, by and large, the most fruitful type of application we encounter. We want them to be ideally unsigned, right? That's an indicator of like, hey, if you're not doing this, then what else aren't you doing, right? I call it the litmus test of application security. And then we also like to look for legacy applications, right? So legacy applications are coded with backwards compatibility in mind. And so when they're coded in such a way as to preserve that, reverse compatibility, then they are intentionally foregoing current and more modern security practices, right? And then we move on to things we don't want to include in our data set. We don't want to include components of the operating system. They're likely not a good use of our time. They've been looked at, they've been heavily scrutinized by people way smarter than us, honestly. And we also, in the same vein, don't want to look at software that's been published by a super well-known vendor or super reputable vendor, right? A vendor who's putting out consistent quality and, follows proper security practices. And then obfuscation, right? It could go either way, because obfuscation is basically a big red flag saying, hey, I'm doing something here that I don't want you to see, right? So it's likely still worth the time and effort to look into it, but it's not immediately accessible because there is that initial barrier to entry. So kind of like a recap of some of the initial heuristics when we're going about laying this foundational data set here, right? Is the application running at a higher privilege level than us? We have to always maintain the idea of our operation, our red team engagement when we're looking at these data sets, right? And gathering these data sets. It has to be relevant. Does it have the potential to push the engagement in a new direction, right? Can we predict, trigger, or otherwise instrument the application's control flow? So what I mean by this is that it has to be accessible to our current context in the red team engagement. If it's not accessible to us, then it's of no use to us. And finally, like the attack surface has to be large. Does it have networking capabilities? Does it, expose any inter-process communication? This is somewhat addressed by assessing on the golden image because it will translate from the individual to the enterprise. But it's still good to target applications with a large attack surface. So to recap, right, we are casting a wide net here. We're not doing anything crazy. We are building a foundational data set to use for the remainder of the exploitation process. And this is just the very beginning of the first step, right? So now that we have our data set that we can use, and it contains some potentially vulnerable targets, how can we determine the likelihood of there being an exploitable vulnerability in one of these target applications? So that brings us to automated analysis. I'm going to pass it over to Matt.
Okay, cool. So we have an initial target set, right? We've evaluated everything that's on the system, everything that could potentially be exploitable. We don't have any idea about state right now. We just have things that we can point to. So now we need to take that and start figuring out where the most likely and best use of our time for the most likely exploitable target. So the biggest thing we need to do from a red team perspective is on-target triaging. So on a red team, right, we are not only dealing with the technical limitations of our tools, the operational necessity of what we're trying to get after, but we have detection risk as well. So I can't just say, exfiltrate all targets off the system so I can analyze them on a safe system. I need to do as much on host with as little detection risk as possible. Thankfully, there are tons and tons of tools that help with this. Some more obvious than not. So NT Object Manager is kind of a crowd favorite. So we've got essentially a PowerShell script that can interact with low-level Windows APIs. I've written some custom stuff, Inspect Assembly I'll talk about a little bit later, but there are tons and tons of tools that we can use that make this process very simple if we just know what to look at. But the general gist of this is that I need to know the attributes to enumerate or evaluate inside of a target that will give me a high fidelity indicator that there is a vulnerability that I can exploit. So how do we actually go about doing this? So the first thing, when I started in security, has anyone seen the SANS poster that goes over the PE header and it's got all these blowouts or whatever? It's been around for a billion years. I thought that was the cringiest thing I've ever seen. People had it hanging in the sock or whatever. I was like, oh, that's cool. It's a file format. I totally get it now. There's everything that you could ever possibly want in the PE header. You can infer so much. If I see RPC RT4.dll in the import table, that tells me like a pretty big piece of information. Like that's that does RPC something. It could be a client, it could be a server, but it tells me that I'm dealing with RPC, which is a huge attack surface. Things like DLLs, right? Jack talked about that being a lower priority because it needs to be loaded into a parent process to be targetable. But what does that DLL do? The exports are usually named. Can I infer based off of their name that they're useful or not? More than likely, yeah. And then other things that are kind of nestled down in there, like the CLI header can just definitively tell me if this is a .NET application, meaning I can reverse engineer it or decompile it essentially directly into source code, and it becomes code review at that point. Same reason here, like Java is the exact same, right? We can decompile it from its intermediary representation into what equates to source code. But also, we've been focusing on like the file side of this, right? Like we have an executable, we have a driver, we have a script, and it does something that could potentially be bad. But if we're just looking at it from the file aspect, we don't really have a lot of runtime context. So just stepping outside of the binary itself and saying what's happening on the system, things that are simple, right? Like what ports are being listened on by applications, what COM classes are registered on the system, what RPC endpoints are registered, things like that, right? Like they're tied to applications, but it gives us a better viewpoint of what's going on that we wouldn't easily be able to identify just by looking at the file itself. And then even stepping further outside of that, like looking at components of the operating system that are interacted with indirectly by these applications. So a good example of this is the system handle table. Not knowing anything about the applications running on the target, I can now evaluate what handles are present in there. And Jack will talk a little bit about how we would use that. So tooling considerations. We are constrained wildly in this, right? Is anyone here a red teamer? A few? Okay. So for those of you not aware, right, like we have a C2 agent, an implant, a process running on a target system that we've compromised that we're operating from. And that process, that beacon, like to refer to it in like Cobalt Strike parlance, is responsible for executing all of our post-exploitation tasks. And the way that we do that is through usually like extensions of that by loading secondary tooling. So long time ago, this kind of shifted to PowerShell, and a lot of tooling was built around that. PowerShell got insanely dangerous to use from a detection perspective, thanks to some innovations by Microsoft. Moved over to using other .NET language, C#, extended that out, same deal. More telemetry happened. It became really, really difficult. Now everything is kind of running in memory, in the self-contained process using C, C++. If you ever heard of like BOF files, that's why. But we're constrained by the language because there's indicators related to the language usage itself that can tip people off to what we're doing. So I can't just easily say, there's this amazing tool, I'm going to run it. Like I could get caught doing that, and in the process of trying to make one step forward, I get us entirely evicted out of the network. So it's an untenable risk. We also don't have like a GUI or anything, right? Like we can't just deploy Procmon and let it run and just hope for the best. I'd love that. That would be awesome. But realistically, we're never in that perspective unless we get very, very lucky or like steal something, which is probably not going to happen. So all of these negatives out, right? Like we gain a huge amount of context. I'm not downloading an application off of the internet, installing it on a VM and just looking at one application, right? I'm on the target already. Like, is this application running? Is it accessible? Like I know that information going in. I can do runtime analysis for specific configurations that the target environment may have that I might not be able to replicate. So I have a direct, I know exactly how the target's going to be configured, and I can directly query it, and then I can do all my analysis based off of what the real world is going to look like. So there's two primary approaches when we're looking at this target set to find initial indicators of vulnerabilities. And this is kind of split based off of how you want to approach it. You search for a single bug class against a large amount of targets. Who here is like bug bounty hunters? You do like any bug bounty stuff? A huge return that people are seeing now is rather than trying to be a jack of all trades, master of none, you get really, really good at one bug class and you search all the targets for it. And then you end up just making a ton of money, hopefully, on one bug class. So if you're really good at exploiting that one, and you find it in a whole bunch of applications, we don't really care about what the target is. We just care about the outcome. So like that's a good place to start for us. But let's say there's an application that requires like special attention. It could offer us something very, very important. We could look for any exploitable bug in that application. So since we're just looking for a means to an end, right? Like all of this is a very focused view on a very, very small component of an operation. I don't care what the target is. All I care is, can you get me elevated privileges? Can you facilitate lateral movement through remote code execution? Can you establish persistence for me in a novel way that's not likely to be detected? So since we don't care about the target, we'll start with the first approach of just looking for singular bug classes against all targets. If that doesn't yield anything and we exhaust our list of bug classes, then we'll pick a high-value application, large attack surface, a highly privileged, so on, and then just look for anything that we can exploit inside of it. So what bugs specifically do we look for? Here is a list of all of the things that we have routinely exploited on red team operations over the past while. They can roughly be broken down into 4 categories, but I want to say, I see a lot of cameras coming out. This is not exhaustive. This isn't what you should be looking for, right? This is what we've been looking for. We've done a lot of .NET development, so we know that ecosystem very well. Done a lot of COM programming and RPC programming, know that ecosystem very well. So this is what we look for. But I want to emphasize the fact that, like, you can put literally whatever you want. If there's something that you're really good at that, like, I have no idea about, like, I do a lot of driver exploitation. There's one thing related to a driver thing up here. It's whatever the team can do and reproduce very easily, because the return on investment problem is a really hard thing to solve. So when we break these down into 4 categories, we start with inherent security weaknesses, things that are fundamentally broken with the technology that cannot be done safely by the developer. A great example of this is insecure .NET deserialization with binary formatter. Microsoft explicitly says there is no way to do this safely. Guess how many people use binary formatter today? Like everybody. Like there's a C2 agent for Mythic that uses binary formatter under the hood. It's safe because it doesn't have user mode or user supplied input fed to it, but still using it. It's commonplace. It's really easy to use, so why not just use it if there's Stack Overflow references to it? The second one is improper access controls. Essentially, a DACL, a discretionary access control list, was not applied appropriately to a secureable object on the operating system. You did not restrict access to this thing that you should have. So this is actually the crux of DLL hijacking. DLL hijacking doesn't really have anything to do with like a missing dependency. It's the fact that you can write to somewhere in the safe DLL search path. So if there's a writable directory in there, that's an improper access control vuln that happened to result in sideloading or hijacking. Third one, sensitive method exposure. Essentially, there is a legitimately safe piece of software, technology being used, that exposes some developer designed and implemented feature that it does something unsafe. So imagine a RPC server that exposes a procedure that will run any command that I specify as system. That's a real story. It runs a system. It does super important stuff for a big software vendor. But it's just doing something unsafe and letting anyone do that without questioning whether or not they should be able to do about that. And the last one is the more traditional one. It's just bad development practices. Essentially, a developer didn't do what they were supposed to do. This is the traditional, like, you use stir copy in 2023. Like, it's, you should have done it the right way, but you did it the wrong way, and now you're going to pay the consequences. So it's an implementation issue. So an example of this analysis flow can essentially be distilled into a very simple flow chart, right? I have my initial target set, and we'll talk about just DLL hijacking. What filters do we have to pass through to determine if this is exploitable, and then what the value is? So the base requirement for a DLL hijack is that a directory is writable. I need to be able to write my payload DLL to that target directory. If it is, does that application now run as a higher integrity level than me? Sorry for using a lot of like Windows terminology. We just target Windows a lot. Linux is a little bit out of scope for this one. But now we're talking about evaluating what the value of that target is. So if we've already identified the requisite conditions for a vulnerability to be there and be exploitable, Now we're talking about what it's actually going to yield us. So if it's running in a higher integrity than us or as a different user than us, that's a privilege escalation or at least an identity shuffle. If that directory is remotely writable, like let's say the $C share is accessible on a target and I can write to it, that's remote code execution. That's lateral movement and privilege escalation with a DLL hijack. It happens. But we break these down essentially into, can I evaluate the attributes that need to be present for there to be an exploitable vulnerability, and then evaluate what it could return to us in, can this get me LPE, RCE, whatever we may be after. More complicated bug classes follow the exact same template, right? For .NET remoting, is the target a PE file? It has to be, because there's not really like a .py C# thing. Is it .NET? You can't have .NET remoting without .NET. Kind of makes sense. Then very specifically inside of that, does it call the .NET remoting server class? And on that, we know definitively if it implements it or if it calls it, this is a vulnerable target and we can exploit it. We just need to collect a few details about it. And then we start evaluating it. High integrity, listening on all interfaces, and so on, right? So we determine that requisite condition, and we evaluate what it'll get for us. So to recap this, right, we had our initial target set, and we do some on-target analysis to figure out of those target applications, which one likely have something that we can easily exploit based off the bug classes that we want to target, and will return to us something that is operationally relevant. So the next question we need to answer is, how do we verify that there's an exploitable vulnerability in that target application? And that comes down to manual analysis. So our primary concerns with manual analysis are validating the information collected during automated analysis. The tooling that exists for automated analysis is usually pretty correct, but we need to be absolutely sure. That way we just don't go chasing our tails on this one. Then collecting any new information we'd need to determine exploitability. Is there something that we couldn't assess during automated analysis that we need to know? A good example of this is, I'll harp on it again, RPC. All of my automated analysis realistically right now can tell me this is an RPC server. It exposes n number of procedures. It will not tell me the nature of those procedures. It will at best tell me their names, but I can't really get any information about what the function actually does. So I need to figure that out, right? And then the last part is just collecting the information we need for exploitation. Some of this stuff, like automated analysis, happens, and we don't need to do this step. If we did need to do it, it would be collecting like a tiny, tiny little piece of information, but that's it. Other times, like this is where the bulk of the work happens. Driver, RPC, like anything related to insecure method exposure is where we would do a lot of this. And this is where the more traditional reverse engineering takes place. This is where you're going to be opening IDA or Ghidra and reviewing the source code of the application or the decompilation of the application, so on. So the objectives that we're looking for when we do this are very targeted based off the bug class. We don't want to spend a lot of time doing reverse engineering. This is the very time-intensive and very expensive process. It requires a specialized skill set or specialized knowledge. Like you can know the bug class really well, but now you got to know how to use a disassembler. You need to know how to review decompilation, P-code, and Ghidra. Like it's a secondary skill set. It's very expensive to do. So we want to be as targeted as absolutely possible. So if we are going to say like DLL hijacking, we know that's possible through automated analysis. Like we have proven that. But there's other considerations, right? Run a red team. I can't crash the target application. Like that is a hard no-go. I can't let the user know that I did anything. So if my DLL doesn't supply the same functionality as the original one does, the application will come up blank. Like there's a famous DLL hijack in an imaging tool called Rufus that if you hijack the DWM API DLL in it and you don't supply the appropriate functionality, it just makes a white box on the screen, which is really, really bad for us because all of a sudden this application that has historically always worked now doesn't. .NET deserialization gets more complicated, right? Like how do I know that I can control the input to that dangerous deserializer? I can't do that through automated analysis. That's control flow analysis, and right now we just don't have the tooling for it. And then more complex is the sensitive method exposure. All I know is that methods exist. I don't even know if they're sensitive at this point. I can tell maybe by their name, but not much else. So the tooling that we use is super simple. Theoretically, if you use the free version of all of this, it's free. These cost $0. It's not, notice that there's not a lot of tools here, right? We're not investing in like huge fuzzing infrastructure. We don't have, like crazy solvers. Like there's nothing complicated up here. These are all like garden variety tools. We have disassemblers. Ghidra is free. Decompilers, .NET, ILSpy, DNSpy, EX, free. Debuggers, WinDebug, amazing tool. Totally free. It's just out of a Microsoft store. And then like system observation tools, right? Like, can I just observe what's going on in the system? So Procmon is my favorite. Just having access to those tools is pretty much all you need. But what I really want to convey here is that you don't want to have this huge tool chain that you have to use and constrain yourself to using these expensive technologies or needing to have this crazy engineering overhead. I haven't fuzzed anything in 8-9 years and haven't needed to define any of these and haven't had any issues with it. So the heuristics for this step can kind of be broken down into two sections, untargeted and targeted. So untargeted heuristics are things that, like, I don't really care about the nature of the application itself, but like attributes of the application more generically. So traditional code smells, right? Developers just doing stupid stuff in the code generally. Like there's a safe practice or a proper practice of doing something, and they've violated that standardized practice in favor of doing something ridiculous. Jack's example in the slide is using sleep 10 versus like using a proper synchronization primitive. I'm totally guilty of that. Like you need to pop a message box in a DLL, but it exits before it like actually has a chance to pop. I've absolutely slept for 3 seconds just to wait for it to do it. Like, I'm not going to point fingers because there's a few pointing back at me. Strings, right? Like, strings are super, super useful because they give you a huge amount of context about what the application is doing. And I could just very easily, there's a popular antivirus in Southeast Asia whose driver, instead of using comments, they use debug print statements, which use strings that are included. And it literally tells you the line of the file that you're reading in the source code. It's great. Super helpful contextually. And the last one, and more interestingly, is just interesting functionality that's exposed through some attribute. Like if I look at the import table and I see that you're calling like crypt protect data for interacting with DP API protected blobs, I know that you're dealing with sensitive data. Like I just know that based off the nature of that API. Memory operations, like are you allocating memory in a remote process for some godforsaken reason? We can infer a lot of this information just generically. I don't really care about what the application is or does right now, but other things that indicate that I need to seriously look at this. Because if I'm dealing with one application that imports, RPC type stuff, COM stuff, data protection stuff with this huge surface of things that look like they interact with something very sensitive, I'm going to target that over something that has like a bunch of weird like kernel-based stuff that may or may not, like, is create name pipe or create file just inherently more valuable? Probably create name pipe because it introduces an attack surface. Not to say that create file is useless, but we can tell just based off the nature of these, if it does something interesting, it's probably worth looking into. But the targeted heuristics is where we really start getting into the focused effort of this process. So take insecure deserialization. Right? There is a function that calls a vulnerable deserializer that will take, hopefully, my data and do something bad with it. And if I can influence the data going into the deserializer, I could potentially trigger code execution. How do I know where that deserializer is called? How do I know that I can control the input going to it? Is my input changed in any way in going to it? Is it validated at any step? I can verify it during this step. Are there preconditions or external factors that will affect my exploit? Like, is there a secondary check for one that we've seen is the application will validate that the client application that connects to it is signed using their certificate. So that means I need to inject into one of their other processes or a legitimate client in order to exploit it. And then is the vulnerability relevant, right? Like when I exploit this vulnerability, assuming I can find it and can exploit it, is this going to get me something? Like if I really, really, really need a privilege escalation and all this is going to get me is persistence, is it worthwhile to spend my time on right now? Probably not, right? Like we have a very explicit goal and this is just a means to an end. I don't really care about finding the bug. All I care about is the outcome. If it's just going to give me persistence, it's probably not useful right now. Not that it's not generally useful, just not contextually useful. So to recap this section, right, we had this filtered target set of like qualified targets, we'll call them. So they have a high fidelity indicator that there could be a vulnerability in here, and I've either validated that through automated tooling or I needed to collect some additional information to know that for sure. And at the end of this, I have a group of verified targets, usually just one, because by the time that we get to this step, if we hit on it, we're going to exploit it immediately. We're not going to take all of our qualified targets from the automated analysis step and then do this for every one of them. We're going to go with the first one that we hit on. So the last bit of this is how do we convert this vulnerability into progress towards our overall engagement objectives? Again, remember, all we care about is getting back to the operation. Like we need to go steal the Colonel's secret herbs and spices. We need to get the Coca-Cola recipe. We don't really care about anything related to this vulnerability after this step. So this is exploitation. From the red team perspective, we are concerned with two things that really kind of boil down to one. I don't want anyone to know that I'm exploiting this target. That is the chief concern. That means I don't want to have to drop my exploit to disk and run the risk of somebody picking it up, like an antivirus scanning it. I don't want to have any visual indication that the exploit triggered, like if I forgot to take my message box shellcode out and shipped it to the target. I totally haven't done that on a real op and got burned doing that. I don't want to crash the application, or I don't want there to be any indication that I was ever there, because I still have to carry on the rest of this operation. I have an entire team working with me. I've got a client breathing down my neck. Like there's things at stake here that I can't really afford to compromise. But the great news about this is that we don't really need an overly robust exploit. We don't have to support all versions of this application, all versions of the operating system. Like let's say I'm requiring like some specific OS version offset. Well, if we're going back to the idea of a standard image, they're all probably running the same patch level. Like they're running, the latest version of probably Windows 7. I could just say, like, I will support the offset for this version because it's what I've observed. I don't need to support Windows 2000. Like it's just not realistic, so I don't have to factor for that. I also don't need anything crazy because it's going to get fed through a C2 anyway that can't support complex stuff. I don't need a GUI because I literally can't use one. So the exploit development cycle for this realistically is not overly different from a traditional one, but we're focused on speed here, right? We've identified and qualified the target. We have something that we're going to go after. We have the supporting information. And then we just build a basic exploit in one of our supported languages, whatever our C2 will let us use, PowerShell, C#, C, C++, whatever we got to roll with, that's what we'll use. We'll deploy the application in test VM so we can verify it if we need to. Sometimes we don't even really have to do that. We'll tweak it as necessary, then we'll test it over C2. I'll deploy a C2 agent in my test VM. I'll test it over C2 to make sure my actual exploit script works. And then we're sending it. Like that target's getting popped, and then we're back to business. So a case study here. This is a bug that I found in the Alienware Command Center application. This is a super interesting one. Does anyone have Alienware hardware? They make like laptops, monitors, a ton of peripherals. This is fun because if you have a Alienware device, they come with a USB 3.2 cable. And when you connect that to your computer, without telling you, it automatically installs this application. Super awesome, right? I love when vendors just install stuff on my computer over a cable. Cool. So if you have Alienware hardware, you might want to check for this. But essentially, it's an application that's really kind of just meant to change the color of LEDs. I don't really understand its usefulness, so yay. But it's a .NET application. So one day we were sitting kind of on a chat and just poking around. I'd got a new computer or whatever, and I just wanted to poke around at some stuff. So I listed all .NET processes on the system. I have a GUI session at this point because it's my personal computer. So I load up Process Explorer, and I'm looking, and there's a filter that you can apply to highlight all .NET processes. Just applied that. Found a few that were running a system. I'm like, okay, that's interesting. So I have my target set, right, of all of these .NET applications. And I use a tool that I wrote called Inspect Assembly, which, again, it's .NET applications. When they are compiled, they live in intermediary representation, MSIL, CIL, or just IL, where that can be converted almost exactly to one-for-one source code representation. So in that, it's essentially like easily reversible. You can treat it kind of just like plain text and parse it linearly. So this tool, all it does is linearly parses the CIL, looks for a call to a dangerous function that I've specified based off the bugs that I know how to exploit, and will return back to me the function in which it's called. So it immediately dinged this server application for .NET remoting. It calls a remoting server class. So I'm like, okay, .NET remoting is very, very easy to exploit. I know how to do it. I've done it a billion times. I'm just going to dig into this. And sure enough, it has a name pipe that's accessible to everybody. Thankfully, it was scoped to the local host and not everybody. But all the details that I needed for exploitation were there. And all I had to do was open it in dnspy, collect those details, and then I was ready to go. So I had it on my personal workstation. I used a tool published by James Forshaw ages ago called Exploit Remoting Service. It's still the best tool for the job. Ran through essentially the steps in the README to get it to fire, and all of a sudden it did. And I got a system level process for what I wanted. It was like Notepad in the POC or whatever. But this is deployed in every customer where there's Alienware hardware. And good thing there was a pandemic where everybody started working from home and bought all their new stuff with their home office stipend. That meant those nice ultra-wide monitors that they plugged into their work computer. And now anybody anywhere with Alienware hardware was vulnerable to this. So thankfully they fixed it. They ended up removing the entire remoting server implementation. So it's good now. Make sure you're updated. I think it automatically updated actually. But this is just one example of like, you can apply this process literally anywhere to find stuff. It's just a filter.
So I'll be pretty quick about this one. But this is a local privilege escalation that I found in Eternity Agent last year. Eternity Agent is a performance monitoring application developed by Riverbed. So with a target identification stage, instead of looking at the files or the processes, I looked at the handles and on the system, and I did that by calling NT-query system information with the system handle table class. And what that gave me was a list of all handles present at that point in time on the system. Using automated analysis, I applied kind of the same way of thinking here, right? We want to filter by relevancy, so we filter on object type. The relevant object types are going to be process objects, thread objects, token objects. And then we want to filter by accessibility, right? So we filter on access rights. Can we duplicate this handle into our own process? Can we access it from a medium to low integrity process? And so after applying that automated analysis, the subset that was left was a single handle, right? It was a system process that was exposed into medium integrity level processes. It was of process object type. And so in this case, manual analysis was not really required at all. I didn't have to necessarily verify anything at a reverse engineering level because it was all available through basically runtime metadata. And then going on to exploitation, right? It's not complicated. Really, 30 lines of code, duplicate handle, call update thread proc attribute, and then create process, and it can allow you to create the child process using that system handle that you duplicated into your process. So wrapping up, this is kind of the full chain exploit process that we go through. Building an initial viable target set is not hard. It's not rocket science. It's basic file system and process enumeration. It's analyzing metadata that you have access to, and consequentially applying filters based on file type and characteristics. Automation can make our life easier to varying degrees, right? It's not always useful, but when it is, as we've seen previously, just with this Eternity LPE, it can potentially make manual analysis like obsolete, right? But in most cases, manual analysis is required and to verify our hypotheses and ensure that we're staying on track in terms of operational context. And then I want to emphasize that exploitation is not always complicated, right? When you think of exploits, some are very, very complicated and very difficult to understand, but often we're using these as a means to an end, and therefore, they don't have to be super complex. So, if we have any time, I'd like to open it up for any questions.
I think we have literally 30 seconds.
Thank you, Matt.
Yeah, I think we're
very great
right.
talk.
Anyways,
applause for them. We have time to take one or two questions from you, if there's any.
If you also
can you come with the mic here?
Yeah, we'll be
these are
on
not
the way
up
after
here.
the talk.
Okay, sorry. It's okay.
Sorry, yeah. What tools are you using for the initial triage and automated analysis? Like after you get the result from the tool, how are you looking through all that data and coming down on engagement?
Yeah, so that's an interesting problem. Right now, it's a lot of manual effort, right? So Inspect Assembly, the tool that I wrote was entirely unstructured output. There's kind of like a renaissance happening in red teaming right now where structured output actually matters because there's secondary ingestion pipelines like Nemesis and so on that can take structured data and contextualize it for us and remove that human element. So unfortunately right now, a lot of it is manual analysis, just looking at it inside of Cobalt Strike. But I think that that's going to change in the not too distant future. And I personally am converting all of my tools to output structured data.
So I have one question. Like when we are checking for TLL hijacking kind of issues, we usually use Procman to check the things manually, like where exactly it's searching for the folders and where the file is not found, something we are looking for the things, right? Mm-hmm. So we need to check the DLL hijacking in the three cases, like while installation, uninstallation, as well as during the update process. So anytime it can happen, right? But every time we need to do the clean install the application one by one every time, and we need to install in the sandbox. So is there any way to automate this process to make ourselves quickly we can get the report, something like that?
So if I understand the question right, you're identifying DLL hijacks during application installation and uninstallation. So I would challenge that with when would you see that on a red team operation? So am I able to preemptively stage a payload knowing that an application will be installed? It's absolutely a vulnerability, but it's not something we would see happen in an enterprise environment or something that we could reasonably predict. Mm-hmm. Is it possible that you could have a secondary compromise of something like Intune or Jamf where you are controlling a push of software to an application or to a system and you're going to exploit that application? Potentially, but if you have that level of access, you could probably do something way cooler with it. So it's, again, kind of like what the value in doing that is, because we ultimately doing vuln discovery like this is the last resort, and I will take the absolute easiest path before I do this. This is like the nuclear option.
Also, it's happened in the Windows, right? In Mac ecosystem, we call it as daily hijacking, right?
Yes.
The same thing. But I don't find any tools to do the things except Objective-C is a website where I can find some tools for Mac ecosystem. Do you have any other tools to check these kind of vulnerabilities in even the Mac?
I don't, but it sounds like a good research project for you.
Okay, thanks.
Okay, thank you. I suggest we stop here. Thanks again.